Okay, to get things started, we'll talk about the Drake scope. The telescope, or the old telescope that's in the observatory, was delivered in 1897. It is 8¼ inches in diameter. It has a focal ratio of about f22.5, which makes it a very long telescope. I don't think there's any secret about that. It is an absolutely excellent scope for looking at planets and planetary nebula and the like. It is a horrible scope for looking at wide-angle nebula and anything that is fairly wide angle. It's fantastic to look at the moon. And in fact, in just 3 months after Pluto was discovered, Dr. Morehouse actually used the scope to photograph Pluto. So it's an excellent scope for planetary research. It was built by Brashear Optics, which at the time was the premier telescope grinding company in the world. And the mount was put together by a company in Cleveland, Ohio, known as Warner and Swasey. Warner and Swasey were the people who put together some of the largest refracting telescopes in the world. So when it was bought and brought to Drake, it was put into the new science building. The science building was constructed in 1893. At the time it was constructed, it did not have, obviously, the telescope, since it was delivered in 1897. So that whole column of floors, which has the telescope on it, was actually constructed after the science building was constructed. As most buildings that were hastily built, it was not on a firm foundation. As a result, every time the trolley passed by, the building, actually the observatory, would shake. This did not sit well with an awful lot of people. Also, the other thing was the fact that there was no access to that new addition from anywhere in the building other than the ground floor. So every time you wanted to go in, you actually had to go in through the ground floor, through that staircase you see there, and actually climb 4 stories. Now, a lot of the complaints that about the observatory was the fact that it was built in the city of Des Moines, where there was smog and smoke and all sorts of pollution. What they wanted to do was to move it out into the country. And they did that in 1921. They moved it to the way out in the country. It was actually the last stop on the trolley. And they moved it into the new observatory that was constructed and dedicated on November 5th, 1921. So the big question is exactly what does a telescope do? Why are telescopes important to be able to look at things in the sky? And to do that, we need to actually start off with a little bit of biology. We have eyes. Eyes are actually an electromechanical device designed to take light and change the light into electronic or electrical impulses. So these electrical impulses would then be travel down the various nerves into the nuclei, into rods and cones that were designed to react to different colors. And then from here, those electrical impulses would be sent on to the brain, where the brain would interpret them. This is the interesting part, because you can have 30 people looking at the same object and get 30 different descriptions of what they're looking at. And this is really a big problem. The task of taking an object and describing it depends upon your experiences, the way you interpret what you're looking at. And as a result, there is something called apophenia, which is the perception of something that might be random. One of the big things we use with apophenia is the fact that almost everything we see resembles a face. If you have a doorknob, it could resemble a face. Electrical receptacles look like a face. And I like this particular cartoon. In 1976, the Viking spacecraft landed on Mars. The orbiter took a picture of this. And of course, everyone went stark raving bananas saying there's a face on Mars. Yeah, it kind of looks like one, but actually this was a mountain range, or actually a plateau, where the shadows and the high areas resembled a face if the sun was at the right angle. Some other objects on Mars that look like something else. This is a real face on Mars. Even has chubby cheeks. Here's the Cookie Monster, Mickey Mouse. And of course, if you drop from a very, very high cliff and you land in the ground, you look like this. And of course, they found the Little Mermaid on Mars. Again, if you look at it from a different angle, it is something completely different. So here we take objects, and due to our experience, we see something else. Now here's something that I think all of you have seen before. Here's the Death Star, and one of the moons of Saturn definitely resembles it. So I guess they went ahead and they built one of those. And of course, here's a little hamster walking around on Mars. And this has been spotted any number of times. Hasn't moved since it was originally spotted, but nonetheless, it's there. Now, this is something which is kind of interesting. Once again, our mind has put together this thing saying this bush is, well, it's not a very nice bush. Let's say that. As you take a close look at it, you can see it doesn't really look very well. And of course, our sky, there are nebulas in the sky that seem to have the same opinion. We have an interesting object in space. It looks like one of the Space Invaders. And this particular Space Invader has its bead on a particular galaxy. So one thing which has come out of this is the fact that we do tend to name some of the astronomical objects with names that kind of that talk about what they look like. For instance, here's the Ring Nebula. And it kind of does look like a ring. And of course, there's the Horsehead Nebula. So I guess it's both good and bad that we tend to look at things through the eyes of experience and name them through something else. Now, what does a telescope do exactly? Well, a telescope actually increases the amount of light that gets to your eye. Just using our eye, we have about 1/8 of an inch of what's actually the diameter of our pupil. If you have a telescope, that could definitely increase the amount of light getting to your eye. And the more light that comes and hits your eye, the more information you can get. As a result, telescopes are merely light buckets. They collect light. And the more light they collect, the more information they receive. As a result, if you look at the same object with the same power, but different diameter lenses, you can see a tremendous difference in what you are looking at. For instance, here is the planet Saturn at 150 power through a 50 millimeter refractor or an 80 millimeter reflector. And as you can see, if we go ahead and increase the diameter of that refractor or reflector, you are getting more information, and as a result, you see things better. The same is true with Mars. At 175 power, you can definitely see a good deal of difference between the 50 millimeter refractor and the 120 millimeter refractor. Suddenly, the polar ice cap is easily visible. So one of the things you need with a telescope is the fact that you have to have enough diameter, enough primary lens to be able to see things better. And one of the big things that you can see is when you're looking at something known as M13, you can see that the larger the telescope, the more stars you'll see. And it's just so important to get a telescope that has some diameter to it. About the smallest scope that I would recommend ever getting is somewhere in the vicinity of about 60 to 75 millimeters. That's 2.5 to 3 inches in diameter if it's a refracting telescope. And we'll talk about the difference between refractors and reflectors shortly. Anyway, the telescopes were invented theoretically, I say supposedly, by a Dutch optical or spectacle maker by the name of Hans Lippershey. He found if he took 2 lenses and put them together, distant objects looked bigger, if not upside down. So he decided he was going to patent this particular arrangement or this particular instrument. And the patent was never granted to Mr. Lippershey because the patent committee thought it was too simple. So this Dutch spectacle maker never got a patent for it, but he did become rich because he made hundreds of these things and sold them everywhere. And Galileo managed to get his hands on one, and he made it a little bit better. First of all, he used a slightly larger lens. Second, he also used a slightly longer focus lens, which gave him a little bit more power. And some of the things that Galileo saw were absolutely mind-bending, at least to Galileo. He saw craters on the moon. He saw how Venus changes its shape. He saw a strange tri-planet, which actually was Saturn, but he couldn't quite resolve it. He noticed moons. He noticed little moons going around the giant planet Jupiter. And in an effort to gain more money, to get more research done, he named these the Medicean moons, so that the Medici family would give him more funds. Well, it didn't work. Anyway, he did look at the sun through some projection means, and he actually made a picture of the sun every day. And he looked at those pictures, and what he found was the fact that the sun was actually a body that was rotating. If you take his pictures and you make it into a movie, this is what it looks like. So how does a telescope work? What are the things that you need in order to make a working telescope? Well, besides your eye, you do need 2 lenses. You need something called the primary lens, the aperture lens, and you also need the eyepiece. So you need the objective and you need the eyepiece. The objective is what actually takes the light and brings it to a focus. It brings the light to a focal point. And the eyepiece sits on the other side of the focal point and will magnify the image that is brought to a focus. So you need both. You need to have the objective, which actually grabs the light, and then you have the eyepiece, which will take the light and magnify the image that's there. So you have the only thing the objective does is grab light. The eyepiece is actually what does most of the work. You can have a long focus eyepiece, or you can have a short focus eyepiece. The short focus eyepiece is actually the high power eyepiece. The long focus eyepiece is the low power. So the power of the telescope is the focal length of the objective divided by the focal length of the eyepiece. So the shorter the focal length of the eyepiece, the higher the power. So you get these really cheap telescopes that have a long focus for the objective, and then they have itty bitty eyepiece that try to get as much power as you can out of that objective, which you find that just simply doesn't work very well. Now, there's a problem when you take light and you actually refract it through a lens, and all of us have seen that. It's called a spectrum. When you take light, put it through a piece of glass, the light is refracted, or it breaks up into a spectrum. And as a result, when you use this simple telescope that just has a simple objective and an eyepiece, you get color fringes. This has a very complicated name for it. It's called chromatic aberration, which is just another name for false color. There's a number of different ways of combating this problem. One way is to make the telescope very, very long. And they've actually had telescopes that were 500 feet long. They would put the lenses on ship masts. So they actually took care of two different problems at that point. They took care of the false color, but also, since they had a very, 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 very long focal length, they would get very, very, very high power. Now, the trouble with getting this high power through this very, very long telescope is the fact that this is definitely not a stable telescope. The slightest wind, you'd lose the image with virtually no breeze at all. Also, you know that if you take two things and you hold them out, they also tend to disappear too. Well, anyway, if you hold them out, they'll actually buffer in the wind. So this is not really a good solution to false color. Now, Sir Isaac Newton, at about the same time, was learning something about optics in his own way. He found that if he built a telescope that used a mirror instead of a lens, he didn't get this false color. So this telescope that Newton invented didn't have any problems with false color. This is called the Newtonian Telescope. Actually, it's called Newtonian Telescope for two reasons. One, you are looking from the side of the telescope, where the image is directed into an eyepiece on the side of the telescope, plus the fact that it uses a mirror instead of a lens. Now, in the 1750s, they found that light could actually be refracted back into its all of its pieces through a telescope by using glass of a different make. In other words, you have two different types of glass. You have a crown type of glass, and then you have a flint type of glass. And because they are two different types of glass, the refracting of the light is actually canceled out. So this is called an achromat. So it's actually a doublet, or two lenses that work together to cancel out false color. Now, if you're looking for which one's better, a um, a refractor that uses lenses that can cause false colors, or a reflector that uses a mirror that doesn't have false colors. Actually, at this particular time, it was very difficult to get lenses that were so precisely polished that they work together well. As a result, reflecting telescopes were being used more because you can make them bigger. And one of the people who was making a lot of telescopes at that time was a music teacher. His name was William Herschel. And William Herschel, in 1774, actually was making more telescopes than he was composing music at this particular point. He built telescopes that were as large as 4 feet across, and build them sometimes out of glass, sometimes out of metal, where he would polish or form the metal into a certain shape, and then he would look at the sky. He and his sister actually made several star catalogs that were well used in the middle to late 1700s. In 1789, Herschel finished the largest reflecting telescope in the world. It had a mirror that was 50 inches wide. That's huge. Had a focal length of more than 40 feet. And you actually had to climb on it in order to be able to look through it. And again, Herschel did a lot of research through those telescopes. Meanwhile, refractors seem to be gaining popularity as they got better grinding lenses and grinding achromats. We have the typical 3-inch refractor right here. And then we also have the not-so-typical 40-inch refractor that's at Lambs Bay, Wisconsin. This is at Yerkes Observatory. And this is this is the largest refracting telescope, actually I should say largest active refracting telescope in the world right now. And this was actually a celebration. You can see Einstein there in the middle. And Yerkes Observatory is rather interesting. Here we have Yerkes, the telescope, looking at something that's relatively close to the horizon. As you can see, the floor is right up, pretty close to the telescope. If the telescope was looking at something that was a lot higher in the sky, suddenly you can see, my God, did the whole thing rise up out of the floor? No, it's the floor that actually goes up and down in response to where the telescope is. So that floor is actually on a lift that goes up and down if you're looking at something either high in the sky or relatively close to the horizon. So as a result, we have a variety of telescopes, both refractors and reflectors that have been built during the years. And it's been just amazing, the things that have come out of this. Now, for one thing which is interesting about building a reflecting telescope, the mirror is actually a parabolic shape. In other words, it doesn't have there isn't really a solution to what that shape has to be. If you are making a telescope mirror and you are grinding a parabolic mirror, you are constantly stopping and testing the shape of that mirror. It would be a lot easier if you actually took a shape that was known, like a spherical shape, and ground the mirror with that. The trouble with that is the fact that if you ground a spherically shaped mirror, you have many focal points. So a parabolic mirror is a very hard mirror to grind. This was actually taken care of in the early 1930s by an optician by the name of Bernhard Schmidt. He developed a telescope that actually had a correcting plate in front of a spherically ground mirror. And as a result of that, he was able to grind the mirror a lot more precisely than a parabolic shape. And as a result, the Schmidt type of telescope was a very wide angle, a very, I don't want to say easy to produce, but easier to produce. And he got some tremendous results out of it. As you can see here, they actually have a film holder in place of a second mirror. So the first uses of Schmidt telescopes were as wide-angle cameras. Now, these are called Schmidt catadioptrics, which is a very long name for saying it's a telescope that uses both lenses and mirrors. What I like to do is we have reflectors, we have refractors, and I call catadioptric telescopes reflectors. That's not official. Also, people kind of look at me strange when I say that. Anyway, but spherical mirrors are actually easy to mass produce. And as a result, the catadioptric or the Schmidt telescope market has blossomed into literally a multi-million-dollar business where you can get a telescope that's a relatively wide diameter, so it's a good light bucket, and be able to see very, very well. They aren't the best telescopes in the world, but they are the best all-around telescopes around. So the big question is, at this point, by the way, these catadioptrics is also what Drake uses on the observing deck, and you can see one of this particular one is made by Celestron. Now, the big question is, why aren't there any refracting telescopes that are bigger than 40 inches? And that's because if you're anything bigger than that, the lens will actually bend, will actually distort under its own weight. So if you're going to build a large telescope, you have to make sure that the lens was designed just to be in one position. Are there any telescopes like this where the lens just remains in one position, but is bigger than 40 inches? And the answer to that is yes, there were. Actually, there was one, and that was built for the Paris World's Fair in 1900. It's a 49-inch diameter lens. This was the Universal Exhibition of 1900 held in Paris, and this particular telescope was almost 500 feet long, and it used a mirror to direct whatever was in the sky down the tube. The lowest power of this telescope was more than 500. It actually, the area in the sky that it actually was able to see was somewhere in the vicinity of about 1/10 the diameter of the moon. So it was a very high power, very narrow angle telescope. It didn't last very long. From what I've been able to figure out, the lens is still around, but it's not being used for anything. The biggest reflector up until very recently was actually constructed in March of 1934. This was the Palomar Telescope in California. The mirror was made of Pyrex, which does not expand or contract. It does not distort very much under different thermal conditions. And this was actually first poured in March of 1934 up at the Corning Glass Works up in Corning, New York. And it actually the mirror actually had a waffle design to it so that it wouldn't take the 40 tons of molten glass that it was originally designed for. It only took about half that, about 20 tons of molten glass. they actually built a mold for the glass to be poured into. And when they did that, the mold actually melted. As a result, as you can see here, you have various areas where the mold actually caused the glass to run. You can see cracks in that mirror. Obviously, they didn't use this mirror. This is now part of an exhibit. They knew that they had to redesign that mold so that it could withstand the 2,700 degrees that molten glass is poured in. So they re-poured it, and as you can see here, you can see the waffle design. 20 tons of glass, almost 6.5 tons, was removed through the grinding process. Oh, sorry about that. And what they found, they actually took the blank, and before they ground it, they had to actually ship it from Corning, New York, to the California Institute of Technology in order to grind it. So this blank, this mirror blank, had to be moved cross country. And it was a good thing they encased that mirror blank in iron, because when it got to California, they found no less than 8 bullet marks, bullet dents in the metal sheath that was covering that blank. Anyway, after World War II, it was finally finished after 11.5 years, and it was finally mounted in the largest eye at that time on Earth. It was the 200-inch Hale telescope at Mount Palomar. You have to remember that this is nothing more than a big light bucket, but it's so big that the astronomer actually rides inside of it. Now, I am sure they would never allow me up there, because I look over the edge and I drool. Well, anyway, that's too bad. Anyway, but that's now, since Palomar was made, mirror making, at least as far as telescopes are concerned, have gone off in 2 different directions. One of them by using a large primary, and the other one by using lots of different smaller lenses. By using a big primary, they could actually grind a lot of the shape into that lens by using something called a spin caster. So they take this virtually zero expansion glass, and they get it in cardboard boxes. I don't understand that. Anyway, they melt it down in a giant oven, and then they actually spin it so that the shape of that lens, the shape of that mirror, is actually formed by spinning that molten mirror, and then they let it cool at that point. So you have a spin caster which is spinning around. I don't know if the inspectors actually spin with it. That would be a heck of a job, don't you think? Anyway, after it's all done, after it's been annealed and it's cool, the mirror is actually inspected and washed. And it's actually ground to a certain. These mirrors are actually relatively thin. They're only made up of maybe about a couple of tons of glass. But they actually have another way of doing this, and that is by using a segmented mirror, where it's made up of flat mirrors that are all computer controlled, so they can actually get all the light focused to a point. So you actually have 2 different ways of making a telescope mirror. either by spin casting a large mirror or by segmenting a bunch of smaller mirrors that are all controlled and all focused to a point. And again, the astronomy world has actually gone in both directions. Here you can see a whole bunch of mirrors that have been made. There is the Yerkes Observatory. There's the 40-inch. There's the Hale 200-inch in comparison. Then we have the Hubble Space Telescope. And you can see that at this particular point, you can see that the larger telescopes, like the large binocular scope or the very large telescopes, there's the large binocular, there's the very large telescope, and as you can see, that one's in Chile. It was opened around the year 2000. The large binocular was in 2005. You have the Keck telescope, which was in 1996, and we'll talk about more of these in a little bit. There is a limiting factor to all this. And that limiting factor is air. You have to look through air, and as a result of that, you have a problem doing that, because the air will actually break up a lot of that starlight. Now, they've partially solved this problem by taking these observatories and putting them on mountaintops, but you're still looking through air. So the best place to be is where there's no air. And of course, that brings up a whole different problem. There's observatories on mountaintops. So if we were to go up where there's no air, then you have the Hubble Space Telescope. But the Hubble Space Telescope, you have a limit to how big that could be, plus the fact that you have to get it up there. I mean, that actually costs more than an earthbound telescope. But you have to admit that the 2.4 meter diameter objective of the Hubble telescope has done one heck of a job. I mean, that's beautiful stuff. Is there anything better that we can do? Well, I say we have to ask Sophia. Let's ask Sophia if there's something better. Oh, not that Sophia. Actually, this Sophia. Sophia stands for Stratospheric Observatory for Infrared Astronomy. This was designed by NASA and the German Space Agency. And it's basically a 2.5 meter telescope sitting in a 747. It's capable of flying up to about 40,000 feet, which is above about 99% of our atmosphere. As a result, it could see infrared. It does a real good job looking at infrared. The trouble is, it's not always, the objects are not always available. The plane is not always available. So you have to have the right weather conditions and also money in order to be able to fly this. So is there another way of making telescopes on the Earth bigger? I'd like to introduce you to Ruby Payne Scott. Dr. Scott was an astronomer in Australia. She was also a tremendous mathematician. She found a way of making telescopes as big as planets. It's an amazing, amazing process. She actually found and worked out the math for something called interferometry, where you take two telescopes that are a good distance apart from each other and you combine their images. Now, you just can't arbitrarily combine their images. You have to use literally the same photons. You have to get the same wavelength from each telescope. Now, with Dr. Payne, she actually used radio telescopes to start with because radio waves are much larger than optical waves and visual waves. So it didn't quite have to be as, shall we say, hair splitting as looking through a regular optical telescope. So she took radio telescopes and she found that if she took their images, and according to clocks, the exact same time, and you combined the images from that exact same time, you can get good results. That meant that because of the curve of the Earth, one of those signal sets had to be delayed. You had to find a way of delaying the signal so that when the computer got both signals, they were exactly right down to the wavelength in sync. Now, this works very well with radio telescopes. As a result, we have radio telescopes that are literally the size of the Earth. So we have to find a way of getting rid of all that information so that the wavelengths are exactly the wave crests are exactly the same. So we have radio telescopes that are extremely large. For instance, this is the Very Large Array, which is in New Mexico. This telescope is actually several hundred feet wide. Then you have the Very Long Baseline Array, which is actually about 5,000 miles wide. And as you can see, one of those telescopes is in North Liberty, Iowa. And it's still working. I was going to say you can go out and visit, but you better call first, because that telescope sitting not too far away from North Liberty is actually in the middle of nowhere. There's a map, just a little bit off Highway 380. So, it's just there, but as a result of that, you can get images like this. This is M87. This is a black hole that's sitting in the middle of a galaxy. And as you can see, the size of that event horizon is that tiny little dot at the end of the arrow. Now, they've actually made a movie out of what's happening at that particular point, and you can see the gases, running from that black hole. And that's what it looks like. Now, more recently, they wanted to get a better look at that black hole, so they came up with another type of radio telescope that uses interferometry, and that was the Event Horizon Telescope. And this one is the size of the Earth. And they actually they actually measured the black hole from that, and they put all of the information together and were able to actually see firsthand a black hole. Now you can see the event horizon, or where the black hole actually begins, is actually about 2.5 times smaller than the shadow. That's that black area. Now, how big is our solar system compared to this? Well, our solar system, there's our solar system, but actually our solar system would be about that big. So this black hole is much larger than our solar system. Now, again, this is a way of using radio telescopes, and in fact, they actually took the hard drives from all of these. What was it? I think it was 200. I can't remember how many there were on this, but there were at least several dozen computers that were involved in this, and they actually had to combine all of this information together at the exact point where all of the information was in sync in order to get this, which is an amazing task. Now, as I said before, this was actually a way of using radio waves, and as you can see, radio waves are much larger than optical waves, but they've actually been able to do it with optical telescopes. And as a result, here's the large binocular telescope using two large mirrors. As a result, the actual size of the that's okay. Sorry about that. The actual size of the mirror taking the picture is actually about that big. Then you have the Keck telescopes out in Hawaii, and the Keck telescope has an effective diameter of about that big. Then you have the Very Large Telescope, that's its name, by the way, Very Large Telescope, which actually has a diameter about that big. So the VLT telescope actually operates with a diameter that's a couple of 100 feet wide. Then you have another telescope, which is, can't read it. This is actually called SHARA. This is a telescope array that's sitting, this is, I believe it's done by the University of Georgia. And this telescope, when they get it all together, has actually been used to directly image stars. The star down here is actually the double star, or the orbiting binary, known as Algol. So it's actually being directly imaged by this telescope. The other, another image that it managed to take, Georgia State University. As you can see, this is what Algol looks like, at least as far as how we see it. The effective diameter of this telescope is 250 meters. So it's huge. And again, we can directly image stars at that particular point. The analogy is being able to read a particular letter on a newspaper from 100 miles away, and I never liked that type of analogy. The other star that was actually directly measured was Altair. Altair, through a small scope, looks like this, through a larger telescope, and then through the SHARA telescope, you can actually see the surface of the star and actually see that, first of all, it's oblong, which means that it is rotating tremendously fast. It has a rotational period of about 9 hours. Compare that to our sun, which is about 25 days. As a result, Altair tends to be a bit oblique. In other words, it's oval-shaped. And a lot of scientists feel that if it was any larger, it would probably pull itself apart. Now, this Altair isn't the first star to be directly viewed. Actually, there are several other stars that have been directly viewed. The first one was Beetlejuice, and that was directly viewed in 1995, and that was by the Hubble Space Telescope. Now, they haven't stopped making telescopes. In fact, not only have they gone to large telescopes, but they've gone to very, very wide-angle telescopes. The Vera Rubin telescope is an ultra-wide-angle telescope. As you can see, the field of view is about 8 times the diameter of our moon, and it was actually designed to look for dark matter. And the dark matter, the reason why it's called Vera Rubin is because Vera Rubin was the astronomer who found dark matter in space. So the Vera Rubin telescope will begin operations in a couple of years and be able to map the sky, looking at various objects, actually looking at the whole sky and seeing how the sky changes literally month after month. Now, there are 3 big scopes that are presently being built. The Large Magellan Telescope, the Extremely Large Telescope, and the 30-meter telescope. And I've said this any number of times, astronomers do not have an imagination for great ways of describing things. So, extremely large and 30-meter, that's just the way an astronomer would think. Magellan, well, they called another telescope Magellan, so that's why that one's called. But as you can see from the configuration down here, one of them uses large mirror blanks, and the other 2, uses the segmented mirrors. So you can see how these telescopes are being built. Anyway, so the extremely large telescope boasts 798 segments in its primary mirror, each one 55 inches across, and each one is individually controlled so that it could actually change the focus of that particular telescope. By the way, you can see right down here, those are cars, which will give you an idea of what the scale of this thing is. Those are tiny little people down there. Anyway, then you have the Magellan Telescope, which is made out of 7 large mirror blanks. And those mirror blanks, actually 6 of the 7 have already been cast and have already been polished. So they're just waiting for the building to be built at this particular point. Both the European Extremely Large Telescope and the Magellan Telescope are being placed on a Chilean mountaintop. Then we have as you can see here, there's the Palomar, Hubble. There's the large synoptic, that's the Vera Rubin telescope. As you can see, it's really kind of a special telescope. Then we have the European Extremely Large Telescope. You can see how large that is, just amazing. Then we have the Magellan Telescope, and again, you can see how large that is. They're trying to work on the 30-meter telescope, but that whole thing is now on hold in Hawaii because they feel that with the burial grounds that are part of the Hawaiian heritage, they can't really grant any kind of access to the mountain that they want to put that on. So right now, the whole thing is on hold until they discover some other way of doing that. But there is still the air that they have to look through. How can they combat that? How can you, I mean, you're building bigger and bigger telescopes, but you still have to look through the air. Well, they found a way around that, and that's by using adaptive optics. They actually have a way of taking the fuzzy light from a star and by using computers be able to make the image steady. They actually take the image and they adjust it so that rather than having an image that is shaking and moving, they actually have an image that is steady. And adaptive optics has been an amazing addition to earthbound telescopes. Just by using that, they have been able to, shall we say, clean up photographs of anything that's in the sky, to the point where they have discovered not only other planets, but they've also discovered the center of our galaxy. They've actually been able to, well, they can't see a black hole, but they've been able to tell exactly where that black hole is. And they do that by sending up a beam of light, a laser, and they analyze how that light is being bent and scattered by the atmosphere, that is fed into a computer, where the computer will actually adjust a mirror, or if it's an array of mirrors, to be able to take that image and clean it up so that you're looking at something that is a lot clearer than by looking at something that hasn't been uncorrected. And as you can see, corrected fields, you can actually see deeper into space. And the way it's going to be used for the multi-mirrors is the fact that they'll have an array of lasers and be able to determine how the atmosphere needs to be adjusted so that they could actually see the sky clearer than you can actually see if you have something in space. And again, here is the center of our galaxy, and they have been able to see the stars that are orbiting the center of our galaxy. The star is where our black hole is, in the middle of our galaxy. And as you can see, there are stars orbiting around it, and they can tell exactly where it is by watching those stars. So it is an amazing tool for the astronomer. So why are they, I mean, one of the big questions here, why are they building the James Webb Telescope? It's not bigger than anything we have on the Earth, but why are they still building it? Why is it going to be launched this October? Why are they going to put it up there? Well, the answer to that is, once again, our atmosphere. The fact that our atmosphere, while it does break up, and we do have a way of making corrections for the breaking up of our atmosphere, we don't have a way of seeing through it. In other words, the atmosphere blocks light. The atmosphere blocks the infrared. So in order to get past that infrared, the infrared spectrum that's being blocked by our atmosphere, we have to rise above it. And that is done with the James Webb Telescope. It is an order of magnitude larger than the Hubble telescope. As you can see here, it is huge. It is literally 8 times the diameter, 8 times the area of the Hubble telescope. That's 16 times the information for that. And it's not even going to be placed in orbit around the Earth. It's actually going to be shot up there, and then it's going to literally assemble itself. All going to unfold. I think the person who actually designed this was an organimist. Then it's going to be placed at L2. And L2, just to give an idea where it is beyond the orbit of the moon, about 1 million miles away. And it's going to stay out there, just orbiting around its null point, around Lagrangian point L2, where it'll stay, well, it could stay forever. Hopefully, it won't break, because there's absolutely no way we can get out there. So when it's going out there, we can't have any kind of help from anything that NASA could throw at it. And the Webb telescope is going to be placed out there. It's actually going to be launched as of right now, October 31st, 2021. So that's it with telescopes. So next week, we're going to be seeing beyond what is visible. Okay, so at this point,